Okay, welcome back everyone after this refreshing break here. And we have two speakers before lunch, and the lunch will be a little bit shorter than announced. So we'll plan to finish at 12:15 the latest. So first off, we have University of Manchester. He already introduced himself briefly as one of the questions to Robert before. So please, Hitesh, small models for big data.
Thank you very much. Thank you for inviting me. I quite enjoyed the previous talk. I apologize, I missed Philip's talk, but I'm going to probably repeat one or two things that Robert said. I didn't know what he was going to talk about, I guess. So apologies for that. I'd just like to acknowledge some people who basically one person definitely had a big influence on everything that I do these days over the past decade, really, and another collaborator of mine. So David Orell, who I work with as part of my consultancy thing. I'd like to thank him. He's really introduced me to a lot of forecasting methods. And generally, he's introduced me to what does prediction actually mean and an uncertainty, etc. And some of his books are really quite a good read. And James Yates for some of the review of some of the slides that I put together. So we've actually written a perspective piece in the Journal of Clinical Pharmacology and Therapeutics that basically covers a few of the examples that I'm going to go through. And these examples are kind of taken from, I guess, my two strands of my life. So one strand of my life is the academic side, where I kind of work with the National Health Service, in particular Cancer Research Hospital. And the other part of my life, which is part of my more industrial upbringing, involving the pharmaceutical industry and biotech. So you'll see a mix here of things that are related to the industrial setting and things that are related to the clinical setting. But hopefully you'll find them of interest. So I guess for me, I've never really understood what the term machine learning really meant. That's why I always tend to put it in quotation marks. A lot of the time, do see people call sort of statistical modeling techniques machine learning, so I usually get confused. And I guess for me, for healthcare and for basically the drug development applications I'm interested in, uncertainty does matter. It matters a lot, and I'll take you through and explain the different sources of uncertainty and how I'm not overly always been convinced that whether machine learning techniques can really handle some of these levels of uncertainty. Then I'm going to talk about some of the examples of the pitfalls of applying machine learning. So like I said, a lot of my stuff is clinically based at times. So I'm going to talk about some of the papers on using electronic health record data and the issues. And trust me, there are a lot of issues that people have not really discussed. We're going to talk about reoffending risk, but we've already seen that from Robert's presentation. So maybe I'll just touch on that briefly. I'm going to talk a little about financial predictions. And then I'm going to talk about something what I call the perfect con. So please do take this tongue in cheek. And essentially what I'm going to highlight is how you can actually combine mathematical modeling and machine learning quite easily actually and create wonderful papers that will quite easily get you into high impact journals, but in general don't really provide much. And I've got quite a good example of that. Hopefully you'll agree when you see it. So I guess there is, so this year I was at the annual Biostatistics conference, which also happened to be virtual, and their keynote or their plenary session was actually on machine learning versus statistical modeling. The reason for this is there is actually a war brewing between the machine learning community and the statistical modeling community to a degree. So if you're an avid Twitter or social media follower, you will see some of these sort of statistical modeling experts really having a go at the machine learning community and vice versa. And I guess one of the problems here is that I guess one of the things that we've discussed in a lot of these discussions is the ability to handle uncertainty. So I guess with statistical models, it's quite easy. You generally specify a probabilistic model for the data. So actually, it's quite an easy thing to do within the statistical modeling framework. However, is that definitely true of the machine learning community and the machine learning methods? I'm not so sure. And I think this is kind of irrelevant. So this ability to handle uncertainty is really important, I guess, in the industry that I work in, which is generally related to pharmacology and healthcare data, where essentially there's so much uncertainty, it's beyond belief at times. And there are many articles on the problem of reproducibility within this field. And this kind of gets to the crux of the problem. And so one article of quite interest to me a while back was this one called The Economics of Reproducibility in Preclinical Research This is predominantly based on what was happening in terms of the pharmaceutical industry, etc. And I think there was a nice quote in here, right, which tells you one of the problems we face when we want to use lots of literature data, mine it, to try and use learning methods to mine this data and then use it to create knowledge graphs, etc., 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 etc. So use some of these complex techniques to look at the historical data. So the analysis of the past studies indicates that the cumulative total prevalence of irreproducible preclinical research exceeds 50%. So basically, what does this mean? Resulting in approximately $28 billion a year spent on preclinical research that is not reproducible in the United States alone. So we have a problem. We have a huge problem of reproducibility within the pharmaceutical industry. And this is kind of important when we're thinking of applying some of these more complex methods to the data sets we have. Can you trust your dependent variable, basically? So thinking about data generation, so thinking about applying sort of, I guess, machine learning or complex sort of prediction techniques to problems. So let's consider things like finance, actually. There's a nice example. What was the price of stock X on Monday at midday UK time? We know what that is, right? You can go and look it up. We have extremely good precision. There's no bias. It's good, right? It's a nice dependent variable. Imagine you're in marketing, did you buy a newspaper on Monday? Well, hopefully that's pretty clear too. The degree of uncertainty around that endpoint is not high. Reoffending risk, does the person sat next to you have a criminal record? I hope in this room nobody does, but anyway, you can see the thing here, right? So there's a degree of certainty around these things. There's little uncertainty in the above, right? And missing data really isn't much of an issue either, especially in the finance industry. You've got reams of this stuff at very, very high resolution. But is that true in healthcare? So my background is predominantly in cancer research and in oncology. And actually the only real well-defined endpoint, as people say in the UK, taxes and death. And so death is one of them, and death in oncology is quite a well-defined time point. You know when a patient's died. However, what's interesting, that's about as certain as you can be. You know when they've died. However, what they've died of kind of isn't always clear. And there is uncertainty in this. And when you work with electronic health record data, what you tend to find is that people will go for the easiest click box option when you're filling in death records. So do bear that in mind. You clearly do have certainty on when they died, but you probably don't have much uncertainty on what they've died of. And there's chances they'll pick more than one option. And this is because we don't really have a mechanistic model of death. We can't really factor out exactly what did cause the mortality. So one other thing that I'm interested in is in cancer is measuring the levels of tumor, right, you have in a patient over time. And there is uncertainty in this, right? So imaging is by no means perfect. It has a certain limit of quantification. And there's uncertainty in that too when you have radiologists. If you were to take two radiologists and ask them to look at the same scans, they would not be 100% concordant. So there is uncertainty. So if I was building a machine learning model to regress against tumor volume or some sort of level of tumor burden, there is uncertainty in that measurement. So I need a way of handling that. Measuring biology, if you think about omics data sets, these two also face problems, right? In terms of the endpoints, the input variables, so measuring this stuff. And we use antibodies a lot, right, in biology so that's strange, right? I mean, how many other fields do you know? I mean, it's quite interesting that we use biology to measure biology. This just creates a whole another level of uncertainty. And if you're a statistician, this is the point where you probably get sweaty hands and start to really panic about what's going on. So uncertainty is vast, right, in both the inputs, so things like omics data, and the outputs, the things you want to regress against. So we have uncertainty in our independent variables or exploratory variables, and we have uncertainty in our dependent variables. So it makes it quite hard, actually. So we have a lot of that, which you don't necessarily see, I guess, in other areas where there is a lot less uncertainty in the things that you're interested in. So I'm going to come back to this concept of reproducibility in science itself. And Nature did this survey of scientists across areas of sciences and asked, well, is there a reproducibility crisis in science? And the answer is yes, there is. So what they did is they interviewed 1,500 scientists from different fields. And they asked about, well, have you ever failed to reproduce an experiment, either your own experiment or someone else's experiment? And you can start to see some of these charts. It's a bit of a problem, right? So let's just look at your own experiment. So you can see that in biology, 60% of these scientists that were reviewed said that, well, actually, they fail to reproduce their own experiments. Generally, it's hard to reproduce other people's experiments, but actually the ability to reproduce your own experiment is actually quite a problem, right? How do you deal with this issue, right? So if you're sat there working with lots of healthcare data and you know that you're essentially mining lots of literature data, how do you know you can trust this stuff? It's really quite hard, actually. And I guess this leads me on to a rather interesting point, which I've started to learn, is that machine learning methods are actually quite good at finding signals in random data. And a nice example of this is I'm quite interested in data reduction techniques. So normally I sometimes deal with at the hospital quite high dimensional data. So my go-to methods are usually, well, it's a single method. It's usually principal components analysis to try and reduce dimensions. But I know there's other methods out there, right? Some quite interesting sort of nonlinear methods, for example. And TSNE, so T-distributed stochastic neighbor embedding, is one of them. But I know some of these more complex methods, which are quite useful for taking high dimensional data and reducing it to 2 to 3 dimensions. They do depend on certain parameters which you have control over, right? So for example, the tuning parameter in this method. And actually there was a nice blog post I came across, which highlighted here, which essentially highlighted how you can use some of these more complex methods to take random data and find structure in it. So it's actually, you can use complex methods on data to find structure in data when there really isn't any. So that's quite interesting. So that was one thing I started to learn when I started to look at some more complex methods to try and look at dimensional reduction techniques for data sets that I've been interested in. So that's interesting, but we do see a lot of positive reports, right, on machine learning, right? We see a lot of reports on machine learning, people comparing themselves to in the healthcare industry compared to healthcare professionals, saying, oh, look how well the machine learning model performed, etc. But is that really the case, though? So I use phrases like rig. So this is basically meaning, well, how do you cheat in a machine learning versus scientist experiment? So here's a nice article, and I quite like a guy called Martin van Smeden, sorry. He has some interesting viewpoints, and they're quite worth listening to. So this was a nice set of articles. So there was an original investigation, which was around using deep learning algorithms for detecting lymph node metastases in women with breast cancer. And then they, biostatistics group, kind of wrote a riposte to this original investigation. And essentially highlighted 3 main issues, right? So this is tends to be a common issue when you're doing these comparisons of people versus machine, really. So one of the key first issues was the physicians were not given all the information they usually receive to making a decision. So basically, the pathologists here were not given access to immunohistochemistry data, which they would normally use. So data they would normally use to help them to make decisions about cases that they are uncertain about. So they weren't given this information. And chances are the reason why they weren't given this information is because actually this is probably quite hard to quantify for the machine learning algorithm, of how you'd include that. The output generated by the algorithm and physician were actually measured on different scales. And actually what you should do if you want to compare, you should measure on the same scale, right? So the model was giving a probabilistic output, whereas the physicians were given a 5-point scale. So is that fair, comparing unlike with unlike? You could also argue that there is over-optimism in the performance of the algorithm, and it was hard to avoid, really. So in this original paper, there are 390 teams, 23 submitted 32 algorithms. They compared those 32 algorithms, and they chose basically the best of that, right? Versus 11 random pathologists that they could find, right? So they're not really comparing the best versus the best. They're comparing the best that they can do using the algorithms versus whatever pathologist you can find, right? So are these really fair comparisons that we're seeing in the literature? And I think this is something to be wary of when you're reading a lot of these sort of competitions where you see people comparing machine learning versus scientists, or machine learning versus humans, basically, in general, in different areas. Another example I've come across, which I thought was quite interesting, is in terms of using electronic health record data for prognosis prediction. So this was a nice article where they actually highlight that the data generation process is actually more predictive than outcome than the actual value of the test. So this was a large data set where they were trying to predict survival of patients. from a essentially electronic health record database. So this will include people who come into emergency wards, right? Or include people who come in often. And generally what you know is that if you're coming into a hospital in the middle of the night, clearly you have a serious problem. And what they found actually, which I thought was quite interesting, is that in majority of these cases, the actual lab test values added nothing to the survival prediction. What was more important is when they came in and how often they came in. So if you're coming in quite often into the system, clearly you have a problem that's causing you quite some distress. And if you're coming in quite often in the middle of the night, clearly this is quite an important problem. So this is just it's quite an interesting article, but yeah, it tells you about some of the biases and the problems that you face when you're throwing algorithms at electronic health record data without really understanding the data generation process. And I think that's one of the points I wanted to get across here. Understanding the data generation process is actually really quite important when you're working with large data sets, I think, especially in the healthcare sector. We heard this before from the previous speaker, so apologies for re-mentioning this. So this was, again, a nice article about the accuracy, fairness, and limits of predicting recidivism, so reoffending risk. And I thought the abstract pretty much summed it up to me. To be fair, in the sense, I guess this is the last few sentences actually. So initially, what they found is that that the widely used commercial risk assessment software was actually no more accurate or fair than predictions made by people with little or no criminal justice expertise. So I thought that was the important aspect of this, is that you could actually just take people and ask them themselves whether or not people with no actual experience in law to be able to classify patients as classify people as whether they're going to reoffend or not, which I think is what led them to believe that you could actually come up with quite a simple 2-feature classifier in the end, rather than using this industrial made sort of 137 feature machine learning algorithm. So I think this is one other important point, is to always benchmark. So don't just jump to the most complex approach possible. You should really think about using a multitude of models just to make sure you actually are getting some degree of extra benefit from using more complex approach. So that was one. I also have a bit of an interest in finance prediction. I've been following this through a friend of mine who I mentioned at the beginning. And sort of artificial intelligence and machine learning methods have been used actually for quite a long time in finance. So they've been used to make decisions about what to invest in and what not to. And there was a nice article essentially a couple of years ago that looked at, well, how well do these things perform? So there is actually something called a Eureka Hedge AI Fund Index. And this basically tracks people who kind of use machine learning algorithms to make decisions on what to fund and what not to fund. And what was interesting is the gains they were getting, right? So they were gaining roughly 7% a year for the past 5 years at the time when this article was written. Whereas if you just invest in the index itself, you would actually get a return of 13%. So you'd actually do better if you just invest in the index rather than using a complex model. And I guess in this article, what they did is they talked to some key opinion leaders and key people who've been using some of these approaches and other people who are skeptical of them. And they said, well, stated some quite interesting quotes, right? So they mentioned that machine learning algorithms will always identify a pattern, even if there is none. And that beating the collective wisdom of the crowd is much more difficult than recognizing facing or driving cars, right? So my person in the interview says, well, my dog can recognize faces, he says. So my teenager daughter speaks 3 languages. And basically said, well, I wouldn't trust any of them to manage my savings, right? So you got to be a little bit careful. And you really do have to be careful when you're using these methods. Decisions sued one of these hedge funds for where they didn't disclose they were using AI automated trades. I think it says my connection is unstable on my machine, but hopefully you're still seeing this. That the investors sued an AI hedge fund because they were disclosing they were using AI methods, and this cost him a load of money basically. So just to be wary. So those are my sort of case examples that I was going to talk about regarding examples I've seen what I thought were quite interesting. And they're summed up in that article that I put a link to at the beginning of the slides. What I'm now going to talk about is a very specific study. And essentially what I'm going to give you is a step-by-step guide on how you create the perfect math modeling machine learning study to get yourself a publication in a high impact journal. Again, like I said, this is slightly tongue-in-cheek, so hopefully you'll take it in that way. But it does highlight a problem, and hopefully you'll see what the problem is. So what would be the first step you would need to do to be able to combine a machine learning and mechanistic modeling exercise? Well, the first thing you would need to do is actually find the solution. So what you want to do first is find a simple solution that already exists. And so the example I'm going to talk about is in pharmacology, where one of the things we're interested in is when we have a new drug, we would like to predict, for example, a certain type of toxicity that could happen in the clinic in patients. So the toxicity we're interested in is something called torsade de pointes, which essentially involves your heart signal not functioning properly, right? So it's a cardiac toxicity. So in the pharmaceutical industry, one of the things that we're interested in is, well, can we predict whether a new molecular entity, so a new drug, is likely to cause this cardiac toxicity in the clinic as early as possible? And there's many people that have been looking at this. So what you're looking at is a pharmacological effect on certain proteins. And these proteins are called ion channels. And you have information on the effect of the drug on the individual ion channels at what we call an early stage in drug development. In the preclinical stage, you want to make a prediction, like I said, in the clinic. And so there's lots of interest in doing this. And this was an original paper where they took a reasonably, what I would call a large set of sample of drugs, but for most people, this is probably not a large sample, of 55 drugs where they have information on the input behavior, input information, which is information of the drug's activity against a specific ion channel. And they then tried to predict or correlate that to a cardiac toxicity output in the clinic. And they found a simple linear model actually worked well. So the point here is that there was a simple solution that existed for this example, and it existed quite a while ago, I would say. So this is in 2013, this is 7 years ago. So then the next step you need to do is, there was a simple input-output relationship, but to make your paper sound better, you might want to try and find some more drugs. So what someone had done, and we'll disclose the paper coming up quite soon, is that they then searched for more drugs to maybe add some noise to the data set, right? But that a simple model will work quite well. So in this previous paper, for those of you familiar with ROC AUC values, they were getting values of 0.95, for example, right? So the area under the curve here was around about 0.95 using a linear model. So you want to add some noise, right? So you try and search for the drugs that have already been previously assessed. So you'll add that to the mix to increase your sample size. So what do you then do? Well, then you need to go and get a mechanistic model, right? That kind of represents the biological situation you're interested in. So I said here that we're interested in the cardiac toxicity. Well, we do have lots of mathematical models of cardiac cells. And in these mathematical models of cardiac cells, they do contain the proteins of interest that the drugs are binding to, that we're measuring in that early point in drug development. And so here's an example of what someone did, and this kind of relates to this example I'm going to talk about. So what you can do is you can take the input data, so the drug affinity for the ion channel, and then you can simulate this mechanistic model with that perturbation. And that mechanistic model actually gives a signal, right? So here's an example, I think, of like 80 odd drugs, right? So those original 50 drugs where we knew there was this simple linear input-output behavior, add those extra drugs. And what you're seeing here is a model simulation, what we call an action potential. And this is the output from a mathematical model of a cardiac cell, right? So this is the signal that it creates, essentially, as a simulation. And what you're seeing here is what you call an action potential. And what you're seeing here is the action potential for all the 80 odd drugs that we were interested in. So what can you do with these outputs from the model? So this is the membrane potential. This is one of the outputs from the model. Another output from the model is something called the intracellular calcium concentration. So let's just consider this a signal. I'm not going to go too much into the biology here. So each of these simulations represents an individual drug, right? So you've got a signal, and what can you do when you've got a signal? As we know, we can create lots of features from the signal, right? So you can essentially create numerous things, right? So you could essentially look at the maximum membrane potential, the maximum calcium concentration. You could extract out some sort of derivative of this signal. You could extract out all sorts of measures, right? And in essence, I think this essentially heat map shows the number of measured. So they had 80 odd drugs in total, I think, in the end. And these are the number of measurements they were able to extract, right? So they extracted lots and lots of features from this simulated signal. What did they do? And so they use the machine. So you've got this input data, which is from experiments about the drug effect against an ion channel, individual ion channel. You simulate your mechanistic model, generate lots of information from the signal that comes from your mechanistic model. And then you combine that with principal components analysis and support vector machines to highlight that you have a really good model, right? So what they found here is that their best model in terms of ROC AUC, so area under the curve, gave a value of 0.96. But we knew there was a simple input-output behavior, right? So by adding on this extra 30 compounds, did it really make a difference? And the answer is no, it didn't. So essentially what we found, so what I found is when I took their data set and essentially just built my standard simple linear model, which actually is mechanistic to a degree. So essentially it's designed looking at the simplest possible mechanism that could be used to explain the data. It doesn't really involve regression coefficients. We essentially give equal weights to the input data. You could get exactly the same ROC AUC value of a 0.96, whatever it is, by simply sticking with a linear input-output model that we had before. So I guess that gives you an idea, I guess, to a certain degree of how it's actually quite easy to combine mechanistic modeling with machine learning and to fool a journal and to find a gullible journal that are prepared to take this. But it also highlights something else. It highlights that when you do have, so in this situation, let's be honest, they already knew there was a linear, the people did know there was a linear input-output behavior. I mean, that was clear. It was known in literature because they did take drugs from that original study before they did this paper. But it also points to that there could well be, in situations where you're seeing this, these sorts of large data sets up from, that have not come from simulated data, but from real world data, there could well be heuristics in there. And those heuristics could well actually have some degree of mechanistic meaning, right? The trick is to find them. So this was a nice study in one way in that they started off with, they knew there was a simple solution. They didn't really tell people too much about it. They tried to add noise and then said, well, we can use mechanistic modeling combined with machine learning to then make predictions. But we have the information here, right? So we have the inverse problem. It's there. We have the solution to it here. So I think that's quite interesting that there could well be heuristics within these large data sets, but finding them is going to be hard, essentially. And for that, what I believe you need is good theory. I'm a big fan of good theory rather than just throwing algorithms onto data sets. Primarily because I'm worried about, I guess, the data sets we're working. We know there's a lot of there's lots of information in the uncertainty in the variables. There's information when things are missing, they're missing for a reason. And understanding these things is quite hard when you're dealing with purely machine learning models, whereas it's not so difficult when you're dealing with statistical modeling techniques. So just to summarize, so I only planned for a half-an-hour talk, so I thought we'd have 50 minutes of questions, but just to summarize, so I guess data sets in my field, in pharmacology, they're increasing in size, that's clear. But we also know we have lots of noise, right? Not just in the input, but also the output. And also our prior knowledge. I talked about the fact we have irreproducible preclinical research. So a lot of people you're collaborating with, biologists, clinicians, anyone with a wet science background or even any other background, you really have to think about, well, how did they gain their knowledge? Were they basing decisions based on rejecting null hypotheses, so p-value tests, p-values, etc.? Were those experiments conducted correctly? We have an issue here of prior knowledge. So I would argue that actually in the healthcare sector, we have far more noise, I think, than any other field, especially in the dependent variable that we're interested in. So that makes it hard, right, in general, I think. Machine learning has probably not been as successful as we think in the literature. Might have you believe. Well, we have a signal, I believe, from this noise does require theory and not just brute force. I think dimensional reduction techniques are quite important. And this is kind of where the original paper we wrote came from. So my belief is that, and it's just my belief, that actually using dimensional reduction techniques, etc., may actually lead us to having much more simpler models than we probably would have had when we start to really think about, well, what data can we trust, etc., etc. It is quite easy to actually combine math modeling with machine learning. And you really have to dig, right, to understand, well, was there really an advantage here and where did these data sets come from? And had they really just taken what was already a simple linear input-output behavior, complicated it just to get a publication in grants? And I guess I'd be very careful with the use of the word machine learning. I think we see the phrase a lot, but it's rare people state the actual methods. And like I said, there is a war brewing between the machine learning community and the statistical modeling community. And I think this is worth reading. So like I said, this year there was a keynote a talk at the annual Biostatistics conference. And the talk was given by a person called Frank Harrell. I mean, if you've not come across this person, his website's absolutely fantastic. There's some brilliant slides in there and a slide deck, and the videos there too. I really would encourage you to look on take a look at this talk on the musings on statistical models versus machine learning in healthcare research. And just before we finish, I would like to, hopefully you'll be able to see this, is share a video if I've got it up here. Where is it? Yeah, you want to see all my emails? I should be sharing my emails. Where's my, I should have prepared this. So hopefully you've got volume. This is from Martin van Smeer. This is the sound of machine learning that is just logistic regression. And I'll stop with my talk there. Any questions?
Thank you. We should
let me turn off the.
Do this.
I'll turn off the video. Sorry.
No, it's great. Being a trombonist myself, I really enjoyed that. Your last example was a movie that, and a motorcycle rider. So that's a good combo. Thank you very much, Hitesh. And it's you had a lot of very nice one-liners here that are rememberable. So let's see if we have some questions. I mean, there will be also, you will be around for the panel talk at the end, discussion, I hope.
When is that? Sorry, I forgot.
14:30, the last half an hour before that we end at 3 o'clock.
Okay, I'll try and make it. I have another meeting to go to, but I'll try and.
Okay, thank you. So any questions at all there?
I have one question.
Yeah, Philip, please.
Yeah, so, sorry. So I was wondering about this. You said that one should try to look for patterns in the data, and so and then construct simpler models. And you said that doing this using theory is the way to go. But I was wondering if you see any advantage in using machine learning in the way that Robert talked about, like Feynman AI or something along those lines, explainable AI methods that would somehow reduce the data or see patterns in the data? Or do you think that's a danger in itself?
I do think that's a danger in itself. It can be. I guess I always think you should use more than one method. So I would never just use one method anyway. So whenever I work on a problem, I never just use one method. That's just not how it works. So I would always start with simpler ideas to start with, and then I'd build up. And then actually I would go for a lot of the clinical applications. I just talk to the clinicians. They generally do have more information than you realize. So I prefer real intelligence to artificial intelligence. I think there's a pun there for you. But you'd be surprised. So there was a wonderful article I didn't mention on here, an example where, again, people tried to use electronic health records to predict prognosis. And there was two approaches the scientists took, again, using a large data set from London. They kind of just went at it brute force, used all the data. And they also built a model asking, well, clinicians, well, what do you think is important? And actually, if you just linearly combine the 20 odd features that the clinicians said were important, that was just as good as using 200 or 300 variables. So the prior knowledge is probably there. It's a case of getting as wide a view as possible on what that prior knowledge is. So yeah, I don't know if that answered your question. So I guess my view is I would always try and use as much prior knowledge as possible before I went into these data sets. That's really important, I think.
Yeah, so somehow encode all the sort of domain knowledge that.
And you might not have to encode it all, right? So some people, I mean, I quite